Our first lesson today is going to discuss functions and function notation. A rule defining functions is the relationship between an input or independent quantity and its output, a dependent quantity in which each input uniquely determines one output. And I think this is the most important portion where we say each input determines exactly one output value. We say the output is a function of the input. Our first example states, is the height of a function of age? Well, we're going to classify our height as the output based on our statement above, and age would be input. So if we think about every time we input an age, is there going to be a different output? So yes, each age determines a specific height. So at the age of 35, I was a height of 5'2". At the age of 36, I was the height of 5'2". At the age of 18, I was the height of 5'2". So each input, so each age, gives me exactly one output. I cannot be more than one height at each age. So at each age, I can only be one exact height value. However, is age a function of height itself? So now if we put them in reverse, so age is now going to be the output and height is going to be the input. So if I input the height of 5'2", I could have been 5'2" at the age of 18, at the age of 19, at the age of 20, etc. So no, this cannot be, because I am each output of the age happens more than one time at each specific height. At a coffee shop, the menu consists of items and their prices. Is price a function of the item? So price in this case is output, and item is input. So yes, each item has one price. So each item gives me one price. However, is item, our new output, a function of price, the input? So if I'm given a price value, I could be given more than one item that could be associated with that price. So thus, this is not a function. Which leads us to want to define what does function notation look like? So in our example above about height is a function of age, we could also write it as h assuming height, a being age, so h is f of a, h is f of a, or h of a. So ideally, this is kind of where we want to focus our energy when we're writing functions themselves. So if I look at example 2, I can say that when I input a function, input an item into my function, I end up with a $sign or a price. Maybe I'll put P instead of $sign. Thus, I could say that the price is determined by the item in which I input into my function. Represent a function that takes an input as the name of a month and gives an output as the number of days of the month. So I'm inputting the month, and the number of days in that month is defined by the output. Thus, the number of days is a function of the month. I could also say that days can be found as a function of the month. Thus, D is a function of M, where M is the input and D is the output. Keeping that same idea in mind, a function n is equal to f of y gives the number of police officers, n, in a town in a specific year, y. What does f of 2005 equal 300 tell us? Well, 2005 is the input, and the input gives us the year. So the year is 2005. This gives us n, and n represents the number of police officers, which is 300. Thus, we could say that in 2005, there were 300 police officers. Example 5, which of these tables defines a function, if any? So we want to again look at the input and how many outputs does each input give us, because each input has to have only one output. So 2 only goes to 1, 5 only goes to 3, and 8 goes to 6. So this is a function because each input goes to one output. -3 goes to 5, 0 goes to 1, and 4 goes to 5. Each input has exactly one output, so this is in fact a function. However, this last example, while 1 goes to 0, 5 goes to 2 locations, 5 goes to 2, and yet 5 also goes to 4. So this is not a function because the input of 5 has 2 different outputs. They're not unique. So not a function. Given the function notation that we have and the table, where Q is equal to G of n, evaluate G of 3. Well, G of 3 then is going to give us our Q value, and n is the input. So looking at our table, n is the input, Q is the output. So when I input 3, the output is 7. Going backwards, we know the output is 6. What is the input? So if the output is 6, here's 6, and here is 6, the input corresponding is both 2 and 4. So the input of 2 and 4 give us the output of 6. Another way we can talk about functions and function notation to determine if something is a function is the vertical line test. So it's a way to determine whether the graph defines a output as a function of the horizontal input. So imagine drawing a vertical line through the graph multiple times. If the vertical line crosses the graph more than once, then the graph does not define only one input for each output for each input, and therefore is not a function. So when I draw a vertical line anywhere on here, notice I am only crossing my graph one time. So each input, each x value, goes to only one y value. So then yes, it is a function. Here I've got a linear line. No matter where I put a vertical line, it's only crossing my graphed line one time, so it is a function. However, our circle, when I draw a vertical line on my circle, notice there are many places in which I'm crossing the graph more than one time. So this is not a function. Since if I look at f of negative 2, I go to two locations. My input gives me both, let's just give it a rough estimate of 2.5 and negative 2.5. So it goes to two locations. So thus it's not a function. Let's evaluate this quadratic here. So given the graph, evaluate f of 2 and then solve for f of x is 4. So f of x is y is the function itself. So I'm going to input my x values and my output is my y values. So if I'm inputting my x value of 2, what is the output value? So I input 2, my output value is 1. Going backwards, if my output is 4, what input gives me 4? My input value would have to be 3. So when I input 3, out comes 4. Express the relationship 2n plus 6p equals 12 as a function p equals f of n if possible. So our goal is to solve for p. Right now I have 2n plus 6p equals 12. So we'll just start solving for p. So I'll subtract 2n. Thus 6p equals a negative 2n plus 12. Divide everything by 6. Thus p equals negative 1/3 n plus 2. I can then say f of n, as it's saying, since that equals p, is negative 1/3 n plus 2. Given the function k of t is t cubed plus 2, evaluate k of 2, solve for k of t equals 1. So we have two things that we need to do here. First of all, I have k of 2. So 2 is representing my input of t. So wherever I see t, I'm going to input 2. This then will give me 8 plus 2, thus 10. So k of 2 is 10, the input was 2, the output is 10. Now we're going backwards. I want k of t. When will k of t equal 1? So I'll substitute wherever I see k of t with 1. 1 equals t cubed plus 2. My goal is to get t by itself. Subtract 2 from both sides. Negative 1 is t cubed. We will take the cube root of both sides. Thus, t has to equal negative 1, since the cube root of negative 1 is negative 1. Thus, I could also say that k of negative 1 is 1. Given the function h of p is p squared plus 2p, evaluate h of 4 and solve for h of p equals 3. So we have two different things we need to do here. Let's first find h of 4. So my input for p is 4. So wherever I see p, I'm going to put 4. 4 squared plus 2 times 4. 16 plus 8. 24. Thus, h of 4 is 24. Now we want to solve h of p equals 3. So I want to solve. We have a quadratic here, so we are going to need to factor. In order to do so, we have to set it equal to 0. So I'll subtract 3 from both sides. And now I need to find two values that multiply to negative 3, but yet add to positive 2. Negative 3 times 2 works as negative 3 plus positive 2. Oops, I'm not positive 2. We need 1. Excuse me. Looking ahead, I apologize. So negative 3 times 1 is negative 3, and negative 3 plus 1 is in fact positive 2. So our magic numbers are negative 3 and 1. Thus, p minus 3 times p plus 1. Now that it's factored and set equal to 0, we can set each factored piece equal to 0. Thus, p equals 3 or p equals -1. Thus, we could say that h of 3 gives us 3, or h of -1 gives us 3. And that concludes our introduction to functions and function notation.